My name is Gerd Schmitz from S.E.A. Datentechnik, Germany. I am one of the CEOs, and my responsibility is in the field of RF communication and V2X testing. We are here at the NI Week. NI Week is for us a very important show to meet US customer, but also worldwide customer in the environment and ecosystem of National Instruments. We work together with the other partners, Conrad, S.E.A. and Megex, in the ADAS IIT group. ADAS IIT has a target to support our customers, OEMs, Tier 1s, research institutes for autonomous testing. We provide all the tools with a detailed knowledge about V2X and other sensors. The detailed expertise of S.E.A. is the V2X communication part and GNSS. So we care about the simulation of V2X, all test and measurement aspects of this technology. And NI Week, as mentioned, is a great success in presenting our new technology to these global customers. I am from S.E.A. in Germany. We are a company working in system integration since more than 25 years. We have focused on different topics. We are very well settled in the NI ecosystem, and we do business in different industry areas. And automotive, you see some examples we do. Today we will focus on the RF test solutions, but we also have specific expertise in wind tunnel control, in specific measurement systems around wind tunnels, and we have built a whole lot of customized test systems over the years. And what we did for V2X and the V2X testing tools is to combine the knowledge we have over the 20 years with the customized test systems and the RF applications to solve the challenges of the V2X testing. Now, a little bit of repetition probably from the presentation before, but why do people invent V2X? First of all, today a vehicle is completely relying on the driver and the information the driver can perceive. So it is quite blind actually, just looking around. So you all know the typical case of the emergency coming from somewhere, and you start turning your head and trying to find this emergency car and the direction it's coming from. Now the goal of V2X was really to put each traffic object, each car, each pedestrian, each motorbike, as you heard before, into a context of the traffic, especially the traffic, and to provide all the traffic-specific information to this vehicle, to this traffic object. And by that, by having this information, the vehicle should be enabled either to inform the driver in the early stages of rollout or later on in autonomous driving to take the correct reactions corresponding to the situation. So finally, you have a car which has ears and some eyes and also can talk to the surrounding environment and the surrounding traffic. The background is clear, I think, at the end. Everyone is talking to everyone. Cows and dogs are not yet in the standards. What you need in order to implement that is a low latency connection between all the receivers and transmitters. And you have an end-to-end relation. So it is not a connection-based communication that is set up. It is some kind of broadcasting, finally, which is implemented here. So the benefits, I think, are quite clear. As also mentioned before, safety can increase. You have better information about your environment. In the high-level view, the flow of the traffic can be improved. Traffic jam situations can be avoided. And if you talk about autonomous driving, you have an additional sensor which gives you very specific information, which is different in quality than the one you can receive by radar or LiDAR or cameras, because these are all line-of-sight sensors at the end, so they need to see the object they're measuring. For V2X, you also get information about cars you cannot see, for example, because it's radio transmission. You can see through walls in a certain sense, and by that enhance the view you have from the traffic, and you have different influence by weather than you would have, for example, by the other sensors. So it's an enhancement of autonomous driving, and we think it is something which is mandatory to have a full view of the environment. Now, talking about the communication, the first basic thing if you want to implement is that if all the cars spread out their information, as we heard, the other cars must be able to understand it. Otherwise, it doesn't make sense. So it doesn't make sense if you have no standard protocol. You have to make sure that hearing each other in the first step, and for that you have communication standard. You heard about one, which is called 802.11p or DSRC here in the States. That is the one which enables, first of all to hear from each other. Now, since around 5 years now, there is a competing protocol, a competing standard, which is called LTE-V or cellular V2X. It has a different communication technology in RF. It performs the same quality of communication. It supports broadcasting, direct broadcasting without involvement of the mobile network. And at the moment, there is quite a bit of struggle worldwide, decisions going on, which standard will be the standard for certain regions. Probably for certain regions, you will have different standards. At the moment, I think the furthest evolved is China. China decided to go with cellular V2X and LTE-V. The point here is, at the moment, it is a very new technology. Chips are under design and in the very, very early rollout phases. And that is a point where we choose a different technology to enable it today as well. Just completing the V2X communication, it's not only about RF, it's also about the content of the messages and the protocol, how to exchange the messages. So you need to understand the message you got. So if I would speak German now, we would be on a different standard base, and you probably would not understand me, even though you can hear me. And for understanding, there are also different standards in the world. You heard about BSMs, which is part of the WAVE standard. There is a European standard on what messages and what content is transmitted. There is, in Japan, there's a specific standard, and China also has its own standard called S.E.A. And in order to implement a full simulation of V2X, you need to implement communication, the so-called signaling standards, and also the applications on top of that, which are also defined in standards. So if we succeed here, we have a car which can hear and speak, that's fine. But still what is missing is the information which is inside, which information is transmitted. So we had already, there is speed, there is heading, and other things which need to be there in order to make sense for the receiver. A very important point, which always needs to be part of a functional simulator for V2X, is GNSS. It doesn't make sense if you receive a message, but you don't know where it is originated. So GNSS is the technology to enable each of the traffic objects around you to know where it is, at what time it is there, and to put this information into the message. So when you receive a message, you know where is the object that has sent it out. So there is some mandatory information. And if that is fulfilling the standard as well, then we have a car which really sees this very specific view of the traffic around it, and it can build a so-called local dynamic map, which means that is a specific view on all the objects around it with information. How are they moving? Where are they moving in a certain sense? And then the receiver can build up his specific reaction to the current status, which could be like we had with the emergency braking, doing an emergency brake on its own, or watching out for some hazardous situation, or following traffic sign information. Now, what are the test challenges around it? I mentioned that we have all the different layers. Now, not for everybody the test challenge is the same. We have different groups working in the different layers. So the chip designers are more in the RF space. We have this transport layer things which affect tier ones, which are important. So messages you saw in the videos before were on the transport layer. The signaling layer is about the specific standards and the content of the messages. And if you are on the highest level, you are on the app level, where you have to take care that your app is functioning correctly, like you wanted to or needed to implement it. So in order to fulfill the different needs, our approach is to have tools for each of the different steps. What is also one kind of application finally is production testing, which does not need to fulfill functional test purposes, but which needs to fulfill measurements and some very basic functional testing. So we started with a very low-cost module comparable to Coda modem. It's just a modem being able to receive and to send messages. That is only available for DSRC so far, also only for one of the standards. That can be used for prototyping, for functional commutation, for testings like you've seen them before. So you equip a car or your measurement system with the ability to participate in this 802.11p communication in some way. Now, if we move into the RF-related thing, if we move into detailed simulation, maybe also with failures, also checking for false okay or false not okay cases, we decided to move into the software-defined radio world. So we have implemented the communication in the NI software-defined radios, which gives us much more capabilities with respect to manipulation, with respect to performance, and also with respect to additional functions. So in the software-defined radio, we have not only implemented the communication, but also measurement functions, channel emulation, and other things that you will see. We can apply these implementations of the communication stack to USRP, which is more a functional radio, which is good for functional testing, like things you've seen before. And we can also use a VST, which is instrument quality RF instrument, which you need if you do calibrated measurements. That is something you cannot do with the USRP. So starting from the bottom up, so with non-signaling testing, you have basically two things which are important. One are measurements, so there are regulations. What is the RF quality? So you heard the V2X communication is standardized globally around the 5.9 gigahertz band currently. That is true for the DSRC as well as for the cellular V2X. So the cellular V2X communication is not in the LTE bands. It is in this 5.9 gigahertz band, which is reserved for V2X communication. So here we have the measurement part, and the other part is the channel emulation part, which means you simulate the propagation of the RF wave in order to check for robustness of your receivers, for the behavior of the receivers, and all the other things under certain conditions which you might not be able to simulate even well in reality, where you need very defined situation. And there are also standards. I'll come to that in a little bit more detail. The test targets in this area are typically quality and performance, robustness of the hardware mainly, and the compliance and the user groups. I mentioned them already: chip developers, system designers, validation and verification. Sometimes if you test, for example, an antenna-chip combination, system integration and production, especially with respect to the measurement of the produced device. Yeah, I mentioned that already. So both standards are working in the same frequency band. They are standardized. Here it's only for EU and US as an example. So there are radio frequency compliance requirements, and in our tool set for measuring, we implement also these standards so that you directly get the information about this wave is compliant or it's not compliant with respect to the EVM, to the spectral mask, or whatever. So that is, as I mentioned, based on the USRP. If you really do the measurements, you need a VST because, as I mentioned, that is a calibrated and traceable instrument. Channel emulation, for those that are not that much in RF, at the end it means when the transmitter sends out waves, it's the orange car in this case, these waves are spread in the environment and they find their ways. So the propagation goes through the dotted line, for example. This would be the line of sight, so the straight propagation to the receiver. or in this case, it's somewhat hidden by rain and by a house. And then you have other waves finding their way through reflection. So that is a typical way. The more crowded, the more equipped the area is with houses and with plants and other things, the more reflection you have. Plants tend to attenuate. Weather has some effect on attenuation. You also have fading effects. And that is what you simulate with a channel emulator. You typically simulate a number of propagation paths. So the reflected one and the line of sight, for example. And in the standard, there are also typical cases like rural environment, urban environment, suburban, and highway environment, which define the parameterization of the channel emulation. And channel emulation, that's the implementation that we have. You see here on the right side 8 columns. In each of these columns, you have all these parameters that you need in order to simulate this propagation. It's all done in the FPGA of the software-defined radio, which has some nice side effect. And parameters that you see is, for example, the gain loss over the path, the time delay, which is clear if you have a reflected wave, it travels longer than a straight wave would travel. And that is then calculated for 8 parallel paths in parallel, so that the receiver finally sees something which is a combination, the mix of all these different waves arriving. As I said, we have implemented that in the FPGA, as we do with the communication stack, and that is the nice effect here is when we want to add channel emulation, we do not have to convert it to an analog wave, put it to another instrument, which reconverts it into the digital space, then does a channel emulation, and then again converts it to the real signal. What happens in our implementation is we calculate the wave which should be transmitted, then we pass it in the same FPGA through the calculation of these 8 taps. Then we finally pass it to the ADC. So you have two conversion steps less, which is good for the quality finally. We could do that also with the USRP and also with the VST. Another nice thing is we can update the parameters with a latency of milliseconds, which enables it to be used with HIL implementation. So if you have hardware in the loop, and you imagine a scenario, a virtual scenario where you are driving along a road and you have a house here, a house there, that would change the reflection scenario over the distance of travel. And that can be changed or adopted by changing these parameters. Anyhow, the trick at the end is to have an environment which is modeled in a way that you have the right RF reflection absorption parameters there, and that your HIL is able to transmit that to our channel emulator. That is something we will work on the future. But for the standard scenarios, we also provide the parameter set, and it's all ready to run. So the effect you can see here, that is a constellation diagram. Typically, for those that are not that much in RF, the dots should be as small as possible, which means you have a very good RF quality. You have no phase shift. And in the right upper part, you see a different setting of the channel emulator. So the lower left one is the one without channel emulation, without any disturbance in between. The upper right one is one where we have line of sight and no line of sight one, tap on, and you immediately see that the pattern changes, which means the wave is distorted in some way. You have phase distortions, you have also some amplitude distortions. And that is kind of the effect that you see if you apply channel emulation. And that is what your receiver finally sees when he's traveling in the real world. So coming to the transport layer, I mentioned that already. 2 protocols, 802.11p being around for many, many years. LTE-V coming up now. What people are interested, people in development, in onboard design, onboard unit design, in validation verification, with different aspects. So one is really the communication, the pure communication, like you need it in functional validation, as we've seen it before. But there are also requirements, for example, for injecting failures in a certain sense, injecting strange communication scenarios, broken messages, blind nodes, things like that. Those that are in the area know about it. And one very typical case is load simulation. With our modem, our hardware-based modem, which in case is a chipset, we are limited to 15 cars. That's the performance it can provide. Now, a congestion scenario has several hundred cars. Because we are software-defined radio-based, we can cover the communication channel by 100%, which means we can simulate as many cars as there would be potentially on the road, which transmit messages. The higher layer standards implement control mechanisms to reduce the transmission rate, for example. If there are too many cars and you have this congestion situation, then the rate of transmission is turned down so that you at least can sometimes transmit some information. And simulating this congestion is something which is immediately available when we use the software-defined radio. And for that, we also have specific test cases. So these implementations, as I mentioned, are available as toolkits, also in the add-on tool store from NI. For this LTE-V C-V2X communication, it implements 3GPP release 14 standard, which is the one which is commonly applied at the moment. There is a release 15, and for that we implement the side-link mode 4 standard, which means that is the communication that V2X describes, where the cars communicate directly with each other without any other kind of infrastructure. From the methodology, the same as DSRC implements. Every node, every traffic object just sends out information, and anybody around can receive it. There is a release 15 out, which is not backward compatible, which to our knowledge is not yet applied, and 16 will be a bigger break for those who were in the keynote yesterday. That will be closer to 5G, and we are looking into that and following that path as well. The stacks are running in the software-defined radio, and they implement the communication capabilities, so sending and receiving messages like a hardware-based modem can do. We can do this high-performance simulation for congestion scenario. We can do very precise, timed by the FPGA replay of packets which were recorded or which are generated and synthesized, and we can do failure injection and extended monitoring. Extended monitoring means yes, we catch everything which is close to a message, even though it's not a complete one, will be available to the test system, and this enables us, for example, also to register wrong messages which are sent out by the device under test, which would not be seen by a chip-based solution. That will just reject it, and you will never see it got a wrong message. In the signaling layer, that is more about dealing with the messages. You see in the upper right part, you have the messages. First of all, the message is a byte block, which you need to interpret. This interpretation is defined by standards, the regional standards in the EU, US, and in China, for example. And then you get, as you see, as you can imagine a little bit, in the middle part, you see the message stream going through. In the right part, you see the single messages, which are contained in these messages, the signal values like speed or heading and all the other things. That is the layer where all the people dealing with apps are interested in. We have implemented these 3 standards for our test system. China is in completion now. And you will see a little bit more about that. You see here the different standards which are applicable, which we have in the test system. Now, application layer testing, we are quite at the level you have seen in the presentation before. So here it is really, does your implementation of an application work correctly? So if it sees a car that does a hard brake right in front of you, does your application inform the driver correctly, or in future times control your car directly by also braking in order not to crash into your system? Here, this is typically tier 1s and OEMs which are interested. So from the tier 1s, for example, Continental is one of our customers I'm allowed to mention here. The point here is the application has to behave conformant to the standards. It has to behave correctly. It does not need to behave if the case is not existing. And there is research going on about extended solutions of V2X, where, for example, you have cooperative exchange of information, for example, the use cases of a car moving onto the highway and there is no gap, so there are plans, there are ideas that the cars talk to each other and tell the cars on the highway, slow down a little bit, I need a gap, so that this can run smoothly, and that is more the research area. We are also involved in several of these. So finally, if we are on this level of app testing, that was seen before, we need to simulate the environment sufficiently, and simulating the environment means all the outer traffic, all the other cars, the traffic signs, pedestrians or whatever, needs to be available as a message stream to the device under test, so it believes it's in this V2X world. It needs to know where it itself is located, so you need GNSS, and you also have the status of the car the onboard unit is in, because that is the content of the messages it sends out on its own. So you need to simulate CAN as well. We have different types of products, turnkey test systems. The whole test system architecture is modular. That's why we can have these different kinds. So depending on the needs of quality of testing, on the depth of testing, it's possible to choose the one which is tailored to the needs of the customers. They are all extendable, they are adoptable, but these are basically open loop functional testing. So these are typically used for the day one testing. You apply something, you check if your device reacts correctly, and then the test case is over. So there is no HIL requirement. If you have more, and for that we have 3 different sizes of products, then we have the HIL-based systems where everything runs in the loop. The models of the traffic, surrounding traffic, and the models of the car is running closed loop, so that you really have interaction and feedback. There also we have 3 different qualities. One implementation here, for example, is in the bigger system, we simulate GNSS per RF, which is needed if you have a full onboard unit, which only has an antenna plug. But if you're just testing the software on its own, it's sufficient for some customer just to have the position information by a bus, CAN bus or Ethernet or whatever, injected into the onboard unit. So you do not need the higher priced RF part. We do that for the 2 basic standards, so 802.11p and LTE-V. And we do it for the different regions. The smallest version, so the basic version in these 2 applications is limited to 802.11p DSRC, because at the moment we do not have a hardware modem for cellular V2X. That is the reason why there is only E and US mentioned in the basic version of the open loop and in the HIL system of the ENOS. Additionally to these test systems, we have the measurement systems for compliance and for end-of-line testing, which require less software functions, but different hardware equipment. So in case of any questions here, we have a booth down there. It is the ADAS IIT booth. You see the logo beside the S.E.A. logo. There's the ADAS IIT logo. We are part of this group, and we'll come to that in a moment. Well, the system looks something like this. This is an example for a HIL system. So you have a real-time part, you have a communication part, a Windows part for the operation. And by that, we can simulate the environment in very much in depth, including congestion scenarios. And in order to be able to do that, we need some kind of scenario simulation. We can attach to different ones. The one we recommend or we have in our product is CarMaker from IPG. So here we can simulate and synthesize any kind of traffic environment. You have a map view like you see up there, where we also can do data management in a far extent. We have the V2X communication path based on our software-defined radios. Position and time we use M3 systems from Stellar NGC. We couldn't adapt others as well. We're using those because they can use all protocols which are available, QZSS, Baidu, Galileo, GLONASS, GPS. They are very high quality simulation. And additionally, we simulate the bus, whatever it is, CAN bus, Ethernet, and so on, FlexRay, and so on and so on. So that is a HIL system, and during operation, everything is operated with around 1 kilohertz, simulating all the traffic running around. and simulating the car itself in a very detailed model. We are using VeriStand here as the core of the real-time system and can adapt to different test environments finally. It's not only about simulation, we also need to test. And in order to test, we can adapt to different environments. So TestStand can be plugged to it. We can adapt Python and Python-related test environments, or we have our own test environment called TestMaster, and it's an open interface. We can adapt to others as well. So finally, to the use case, I think you've seen that already. So there are different use cases, around 20 defined, which define how a car should react in two senses. One sense is in transmitting messages by itself. So if you are in a car or your onboard unit is in a car, you're driving and you have a reason to stop hard, then your car should issue an emergency message, for example. That is the transmission direction. And in the other way, you also need to test, does my car react correctly if an emergency brake comes into me? So do I inform my driver correctly or control my car correspondingly? So here are just two examples, virtual brake light or platooning. Now, talking about the problematic of having these two directions, you see what has to happen. In the transmission case, car deaccelerates, brake light goes on in the high-class cars, so emergency brake light goes on. So your onboard unit in the EU case, in the European case, should send a so-called denim message, which is a kind of event-based message. And if it receives such a message by another car, then it should somehow inform the driver in the day one applications where it's all about information. Later on, it should control braking potentially. Relevant points are here when the message is received, the car, the onboard unit has to check, is it on my lane? Is it in the distance which is relevant to me? Is the car heading in my direction or in the opposite direction? Again, is this message relevant for me? So there happens quite a bit of logic in the app at the end to take the decisions here. Talking about regional standards, they differ. So the EU case says, okay, only if I'm driving faster than 20 kilometers per hour, only then it's valid that I react at all. WAVE doesn't put any limit here. Therefore, the deaccelerations are different. So you see there is also some difference in the local applications and the definition of these. We implement both. And finally, we have the application cases. So we have set up a catalog. It's finalization now about all these different test cases so that it's no need for the customer to first implement all the test cases. We already have the test cases. One point about the test cases is there are really many test cases. It's not about 20 test steps. So first of all, you have to check for receiving and transmitting this kind of message. So you have immediately the double. And then you have all these parameters I mentioned. So it's dependent on the speed. It's dependent on the deacceleration of your own car. Then it's dependent on the distance to the car who sent it out. It's dependent on the direction, on the heading. So if you combine all these in some ways, it's a quite big parameter room that you need to test. And for that, you need an automated test system. That is what we cover here. On the lower right side, you see an image of the car maker environment. So here you define either based on a map like you've seen before, or based on a synthesized road scenario, which sometimes has examples. If you synthesize it and define it on your own, you define the traffic or the other cars. So here the yellow one is the one your onboard unit is placed in. The one a little bit more ahead here, you see it on the road. That is the second car. There can be up to 20, 25 very well detailed modeled, and then we can add all the other 200, 300 cars if you talk about congestion scenarios. Okay, and finally, we have also a data backend where we can put all the data in, where we support very sophisticated analysis. That is a presentation on its own, which I will not make now, so in order to close down. But this is connected to the test system, so you can view what's happening. You can analyze later on what happened, under what circumstances, to complete the environment. So the latest thing, just completing the perspective of V2X as well, where we are also working with partners on. Autonomous driving is not only about V2X. I would not want to sit in a car which is only V2X supported. That wouldn't be enough. It's also about other sensors like camera, LiDAR, radar, the known ones, GNSS as well. And in an autonomous car, these sensors are combined in order to get a very robust decision algorithm and capability perception of the environment. And talking about these things, we have formed a group in Germany called Others IIT, but that's the booth we have downstairs, where we combine the domain expertise of S.E.A. for V2X and GNSS, of Conrad for radar, LiDAR, cameras, and Measure X for data management, for big HIL solutions, and S.E.T. for big HIL test systems and the physical setup. We combine it in one group in order to provide a full simulation environment for autonomous systems with all the aspects, which makes it quite complicated at the end to simulate that completely. So that is some kind of physical setup. So for all sensors, including V2X, the environmental information is simulated depending on the closed loop simulation scenario. And by that, you can do the testing in the lab for autonomous system without the need, and that was very well explained before, to go on the road and then to do hazardous things, for example. Well, by that, I finish my presentation. I hope it was some new aspects as well, and some were repetitions, so now you're expert in V2X. Are there any questions?